Hello everyone, my name is Lucas Silver, and I'll be presenting the paper Dijkstra Monads Forever, Termination-Sensitive Specifications for Interaction Trees. I wrote this paper with Steve Zdancewic, and we did it at University of Pennsylvania. Considering the following program, what it does is it reads in a value from the user, stores it in a variable x, and then prints all of the multiples of x, all infinitely many of them starting from 0, in an infinite loop. So it should be pretty clear to everyone that that is what this program does. So how would we go about writing a formal, verifiable specification that makes this intuitive description explicit? So we can start off by going into this sort of pseudo-Hoare logic style informal specification. So as a precondition, we know that y is equal to 0, and in the postcondition, I just put some English that is pretty similar to what I just said. This is obviously informal, but there are two main obstacles from bringing this into a formal specification. First, it references interactions with the environment / user. In this case, user, but more generally environment. These reads and prints, it's not clear how to deal with them in the postcondition. And it is neither a partial nor a total correctness specification. If it was a partial correctness specification, the fact that there's this while true loop that obviously diverges would make it trivially hold. If it was a total correctness specification, the fact that there's a while true loop that obviously doesn't hold means we can't prove it terminates, so that means it trivially won't hold. Neither of these are what we want, so we need something that is richer, something that lets us reason about what this program is doing as it is diverging. So the entire talk is going to be geared towards figuring out how to write this specification. And we're going to do it in the following steps. First, we're going to talk about how to represent this program using trees. Trees are a Coq data structure for representing denotational semantics. Then I'm going to introduce Dijkstra Monads, a framework for writing specifications for monadic computations. Then I'm going to introduce the extension we made to the Dijkstra Monad framework that allows it to deal with interactive and possibly divergent computations in the rich way that I was talking about before. And then we're going to talk about the particular specification for this program. So first, let's talk about interaction trees. Here is the Coq code defining the tree data structure. So first note that it is defined coinductively, so these data structures can be potentially infinite. Then note it's parameterized on two objects, E, which is a type family, which should be viewed as the type family of events or effects, where I'm using effect in the algebraic effect sense, and R, which is just the return type. And it has three constructors, ret, which just represents a pure computation of type R, viz, which takes in an effect E of type EA, and a continuation K of type A to tree EA. Read this where the input A is a possible evaluation of this effect E, and then K is just telling you how to continue once that effect has been resolved. And then tau nodes represent internal silent steps of computation. We also have this equivalence relation, equivalence up to tau, or weak by simulation, and that lets you remove a finite number of taus from either side of the bisimulation symbol, and doing this allows you to ignore taus except in the case where you have divergence with just silent computation like that. And this approach comes from the paper Interaction Trees by Shad All from last year's POPL, and it forms a monad. So there are return and bind functions we can define on this. Return is just the ret constructor. Bind is too complicated to go into here, but it's closely related to viz. And we can then show this kind of graphic representation of an I tree where we have a lot of silent tau steps everywhere. Then every once in a while we hit an event node, which branches off into all of the different possible evaluations of that event E1, and then each evaluation gets passed to the constructor, which then determines the rest of the computation, which can return a value, it can branch into a new event, it can diverge silently, it can diverge with more events, it can do lots of stuff. So I mentioned before that I-trees have a monad structure. They also have another very important combinator called iter, where iter effectively works sort of like a do-while loop, where f is the body of the loop, and that loop can return two types of values, a value, which is sort of a continuation signal, and a b value, which is a sort of termination signal. And how iter fa evaluates, where a is sort of a initial seed value. First, you apply f to a, and you bind the result to a function that first checks, was it a continuation or a termination signal? If it was a continuation signal, it passes it back to iter f, and if it is a termination signal, it just returns the termination signal. This allows us to very simply define looping constructs in denotations written with I-trees. So it's useful for representing things like while loops, for loops, stuff like that. And I talked before about this effect type family, so let's look at a particular example. This is the state event type family, parameterized on a state type S, and then has this type to type. It has two constructors, get of type state ES, and put of type S to state E unit. These types should be familiar to you if you've worked with the state monad before, because it is the type of the get and put stateful computations. This, unsurprisingly, is not an accident, because we define a function called an event handler that takes elements of state E into state computations. In particular, it takes get to get and put to put. And why we do this is so that we can lift this function to entire I-trees, where if you have that event handler from state E to state, you can lift it to an interpretation function from I-trees over state E to stateful computations that can diverge. So on the left, we've got that program from before in this sort of imp-like syntax. And now here it is written as an I-tree. So this is actually more or less actual Coq code, which makes the control flow explicit and separates out sort of all the different kinds of mutability and I/O effects into these events in the I-tree sense. So now we've taken this program and written it in this monadic form. And of course, we can also interpret away the puts and gets. So we can interpret it into a stateful computation that returns an I-tree that still has I/O events. So now that we've got this computation in monadic form, we can talk about Dijkstra monads. Now, a Dijkstra monad comes about from the interaction of three different objects. First, a monad of computations M, then an ordered monad of specifications W, where an ordered monad is a monad with an additional ordering relation less than or equal to. And think about this ordering relation as specification refinement. And finally, we have an effect observation theta, which has type for all A, MA to WA. Think of theta as a map from a program to the most specialized specification that the program satisfies. This approach comes from the paper Dijkstra Monads for All by Maillard et al. And with these objects, we can write this Dijkstra verify function that first takes in MW and theta, and then a specification little w, a program little m, and returns the proposition theta m is less than or equal to w. This captures the notion that m satisfies the specification w, and thus this is a function that takes in a specification and a program and returns the verification condition. If you're familiar with the Dijkstra Monads literature, the code on the bottom might look more familiar to you. We found the code on the top more convenient for our purposes, but it should be pretty clear how tightly related these pieces of code are. So we do have a few more validity conditions for Dijkstra monads. So at the top, we have this proposition, which basically captures the notion that bind is monotonic with respect to the less than or equal to operator. And then we have these equations on the bottom, which mean that theta is a monad morphism in the sense that it takes ret to ret, and m bind f to theta m bind theta composed with f. You might be wondering why we insist on these propositions to be true, and that's because together they capture a notion of compositionality. The proposition at the bottom is provable from these. So suppose you have a program m bind f, you want to know that it satisfies some specification w bind g. You can prove that by first proving that theta m refines w, or m satisfies w, and then f satisfies g. So this lets you break up your program into two parts and your specification into two parts and write two, in effect, smaller proofs to build them up into this bigger proof. So we've been talking about Dijkstra monads in the abstract, so let's talk about a particular Dijkstra monad, the state Dijkstra monad. First, we've got the specification monad, state spec, which has this type function, s times a to prop to s to prop, which, if you look at carefully, you should realize is actually the type of postconditions to precondition functions. Then we've got these ret and binds we're not really going to go into in depth. This ordering relation, W1 refines W2 for all predicates P, input states S, W2 PS implies W1 PS. And the ordering for these kinds of specifications is contravariant. If you find this confusing, I invite you to read the paper. We have an at-length explanation as to why you might expect this, why this is actually a good intuition. And theta m is the function that takes postcondition posts and input state s to the proposition post holds on ms, which if you look at closely enough, you should see is the type of, or so is the weakest precondition transformer. And this isn't typically how you want to write stateful specifications. You usually want to write something closer to a pre-postcondition pair. We can encode that, and the code on the top might not make much sense, but it will give you something logically equivalent to for all s pre-s implies post-ms, which is what you should expect. So we've made some progress, because again, this I tree on the right is going to be a stateful computation. But we still don't know how to deal with our reads and prints, and we don't know how to deal with the divergence in the rich enough way that we want, so we've got work to do. And the main thing we do to handle this is create the trace spec Dijkstra monad, which is unique to this paper. And in order to build this, we first need to see interaction traces. So what I-traces are linear I-trees, which represent possible executions or possible paths through an I-tree. And an I-trace is just an I-tree over this ev and e type, where ev and is a event type family transformer, which takes an event type family E and returns a new event type family. Here is one constructor that we have listed, ev and, which takes in an effect E of type EA and an evaluation A of type big A, and assigns it the type ev and E unit. So it's linear because of that unit, and it represents what that event is actually evaluated to. There is another constructor that deals with the case where A is empty. We're not going to go into that. And the reason we try to reuse I-trees in this way is it has a few advantages. One, lets us reuse bind, where in this case, bind actually corresponds to a notion of appending and prepending traces. And it lets us reuse our equivalent subtotals relation, which is actually very tricky to get right, and very tricky to write all of the proofs that make it feasible to work with this relation. And we have a new trace refinement relation. TR refines T, which means that TR is a valid trace produced by executing T. It, of course, has a formal Coq definition, but we don't have time to talk about it. So here is a graphical representation of these I-trace notions. So look at this trace. You can see it's linear. You can see its events pair an event E1 with the possible evaluation A. K1 then just gets fed unit, and then it follows a certain path, in particular, this path. And this trace refines this tree because it follows that path. So now that we have our I-traces, we can talk about the trace specification monad. So first we have to talk about how we're really viewing I-trees for this specification monad, and we view I-trees, again, as a sort of set of I-traces. And so when you evaluate an I-tree, you actually get one particular I-trace out, and you do this sort of in the presence of an initial input log, represented by this I-trace E unit here. So your predicates are type I-trace EA to prop to I-trace E unit to prop, where I-trace E unit to prop is a precondition on the input log, and I-trace EA to prop is a postcondition on the output log, where the output log is the final log that you see after the tree is evaluated in the presence of the input log. We've once again got these ret and bind we don't really talk about. We're also not really going to talk about the less than or equal to. And then we've got this theta, which takes an I-tree T to the function that takes in a predicate P and an input log, and returns the predicate that for all traces TR, where TR refines T, P must hold on the log prepended to TR. So, some important things to know about the trace spec. All of the monad laws and Dijkstra monad validity conditions are valid, they hold, and we prove that in Coq. Traces are a familiar way to reason about the possible executions of a program, so that helps us in writing these specifications. Also, if you notice that it has a similar shape to stateful specifications, where the log of events is the state. This is another one of those backwards predicate transformers. And this means that we can define a similar encode function as before. So we've got our code from before, and are we there yet? Well, not quite, right? Because on the right, we evaluate away our puts and gets. So we aren't just dealing with I-trees, we're dealing with the state transform of the I-tree monad. So what we really need is the stateful trace spec Dijkstra monad. And actually, we already have it, because much like the state monad can be very easily lifted to the state monad transformer, the state spec specification monad can be lifted to the state spec specification monad transformer. Then we can just apply it to trace spec, and then we have what we need. And once again, we can define an encoding from precondition postcondition pairs into the specification monad, where the precondition and postcondition is over both the event logs and the states. So we can now finally write it formally. So we got this precondition that y is 0 and the input log is empty, and this postcondition that the final log satisfies the condition that there exists some n such that tr is the trace that first outputs a read event that evaluates to n, and then prints in order all of the multiples of n. And this mults function is a pretty simple cofix point in Coq, not really worth getting into. And then we can prove this by relatively straightforward coinduction. So before we wrap up, I just wanted to go over the major contributions of the paper to encourage you all to please read it. So we introduced two base specification monads, the delay spec for possibly divergent but non-interactive programs. So basically when the event type over I-trees is empty, the trace spec, which we talked about before, which works for divergent or possibly divergent interactive programs. We introduce a verified loop invariant reasoning principle for I-trees without events. We analyze how to encode a lot of precondition, postcondition-like specifications in these monads. And we also introduce the I-trace model, which is a coinductive trace model for I-trees. So there's a lot of future work we're interested in doing in this space. In particular, we're very interested in figuring out better reasoning principles for the trace spec monad. What does a loop invariant look like in the presence of uninterpreted events? Like, how do we write them? How do we prove them? Can we prove them without needing explicit coinduction? What can we do if we know our interpreter follows the specification, but we don't really know anything else? So just to clarify that, like, suppose we had classes of denotations that we know a little bit about, and we want to prove that the programs evaluated under those specifications satisfy some other specifications. Like, can we do that? Is it useful to do that? How well can we scale this to large projects? In particular, can we use this to make a programming logic for Vellum, the verified LLVM project, which now has semantics using I-trees? And how can we transport verified specifications of source programs to verified specifications of compiled programs? Because one of the main uses of I-trees in the past has been verified compilers. So can we leverage this to do this kind of transportation of verified specifications? So I just wanted to end by thanking you for watching this video. If you're interested, please look at the code on the link provided, and look at the paper at the link provided below that. And once again, thank you.